share my screen. So first of all, thank you very much, Juan, for the nice presentation and for the invitation. It's a pleasure to give this talk. So my name is Nicolás Sanchis-Gual. I'm a postdoc at the University of Aveiro. I'm working with Professor Carlos Herdeiro. And I'm going to talk about light in the dark, GW190521 as a boson star merger. So this talk is about this paper that we recently published in Physical Review Letters about GW190521 and Proca star merger. That was done in collaboration with Juan, with Alex Torres-Forné, with Tony Font, with Carlos Herdeiro, with Eugene Radu, and with collaborators. So first, I will try to introduce briefly the topic of boson stars, of bosonic stars, and try to motivate it. As you know, the detections of gravitational waves by LIGO-Virgo and Suncagra, together with the first image of the shadow of a supermassive black hole at the center of M87 by the Event Horizon Telescope, are opening up a new window into the strong field regime of gravity. Even though the data so far is well fitted by the expected physics, this is Kerr black hole and neutron star mergers, it is important to understand if alternative, non-conventional models of compact objects, such as boson stars, so exotic compact objects, can also fit the data, leading to a degeneracy in the emitting sources of the gravitational wave signal, or how much these models can be ruled out by current or future detections. Therefore, obtaining numerical waveforms from these exotic compact objects could lead to their discovery if they indeed exist in nature. So amongst these, the exotic compact objects, I've been studying, focusing on the study of boson stars. So first, let me try to answer these questions. What on Earth, what on the universe are boson stars? So let me say first that boson stars are described by general relativity. They are described within general relativity. So it's not some extension of GR, it's not some modification, it's not some beyond GR theory invoking some spontaneous scalarization of black holes or neutron stars. It's really only a bosonic field which is minimally coupled to gravity, that only interacts through gravity, through Einstein's gravity. Therefore, the Einstein equations will play a fundamental role in the analysis of the dynamics of the gravitational field and can be coupled to these Klein-Gordon and the Proca equations governing the bosonic fields, which describes our bosonic stars. So boson stars were first proposed in the 60s, first by Cobb and then Ruffini and Bonazzola. And we have two types of bosonic stars. We have scalar boson stars, or in short, boson stars, and its vector cousins, which are described by a vector field and are known as Proca stars. So these bosonic stars are made of massive particles with integer spin that follow the Bose-Einstein statistics. They are made of bosons. And at the lowest energy level states, these bosons fall to this energy level state, and they can be classically described by a wave function, which is characterized by the particle mass mu. And we will see that this particle mass mu play a fundamental role in the description of our ball, of our bosonic star. Now, if we consider a complex scalar field or a complex bosonic field with this type of harmonic dependence, I think you can see my pointer, right? So if we have this harmonic dependence for the bosonic field, for the complex bosonic field, then we have a real and an imaginary parts that are oscillating in time with the same frequency omega and with the same amplitude phi naught, while they have a pi half phase difference between them. Therefore, the amplitude of the complex field can remain constant with time. So while the field, the real and imaginary parts of the field are changing with time, they oscillate with a determined frequency, this space-time can be kept static, can be kept time independent. And this is because if we go to the Einstein equations, we have, so the left-hand side corresponds to the space-time description with the Ricci tensor and the Ricci scalar, and on the right-hand side, we have the stress energy tensor. And it turns out that for boson stars, for bosonic stars, this stress energy tensor depends on the square of the amplitude of the complex field, which is constant with time. So even if the field, the real and imaginary parts are oscillating with time, are changing with time, at the level of the energy stress energy tensor, it's time independent, and our space-time is time independent. We can then form stars that are stationary everywhere, regular soliton-like solutions of the Einstein complex massive Klein-Gordon for scalar boson stars, and of the Einstein complex Proca system for Proca stars. It is interesting to note that a real field can also form massive solitonic solutions coupled to gravity, known as oscillatons, but in this case, this space-time is no longer static because the amplitude of the field changes with time. The stress energy tensor is no longer time independent. So there is a leakage, there is a decay of the field of the star with time, of the oscillaton, but the time scale of this decay can be longer than the Hubble time. So if a real bosonic field exists in nature, then these objects could have astrophysical relevance. Now let me show you this short movie, this short time evolution of the real and the imaginary parts of the amplitude extracted at some radius for a boson star. So you can see, so you can see that it's oscillating with the same frequency, with the same amplitude, and the pi half phase difference, so the amplitude of the complex field will remain constant with time. So for fermion stars like neutron stars or white dwarfs, we can identify the Pauli exclusion principle that through the Fermi degeneracy pressure is the quantum mechanical principle that supports these stars against gravity. For boson stars, we can actually identify the Heisenberg uncertainty principle. So it's the tendency of the field to disperse as a wave that will balance the self-attraction of the field itself. And in the very interesting Living review on dynamical boson stars, Living and Palenzuela were able to give an estimate of the maximum mass of a scalar boson star without angular momentum, non-spinning, from the Heisenberg uncertainty principle. And this value that they obtained is close to the actual correct maximum mass that we can only obtain if we solve the fully nonlinear coupled system Einstein Klein-Gordon. So you can see here that the maximum mass is, so this is like the Chandrasekhar limit mass for white dwarfs, but now for boson stars, and it depends on the particle mass mu. So the lighter this particle mass mu is, the larger the maximum mass can be. So if we want a maximum mass between the range of LIGO and Virgo, so between 1 solar mass and let's say 1,000 solar masses, then the particle mass has to be between 10 to the minus 10 to 10 to the minus 13 electron volts, respectively. So we need an ultralight bosonic field to have these astrophysically relevant masses in boson stars. These bosonic stars have been called black hole mimickers because they only interact with gravity. They are only minimally coupled to Einstein gravity. So they are basically transparent to the electromagnetic radiation. So they can mimic some of the gravitational and even electromagnetic phenomenology of black holes, becoming these mimickers. So for example, if we study the shadows of, in this case, Proca stars, and we compare them to the shadow of black holes with the same mass, in this case, a Schwarzschild black hole, then we can see that at least for some models of Proca stars and of boson stars, the blur image of the shadow is quite similar to the shadow of a Proca star with the same mass. So there is a degeneracy. Well, actually, this degeneracy depends on the observation angle. So this observation angle is actually the same than for the M87 star, or the Event Horizon Telescope shadow. But if we look to the shadow from a different angle, you can see that the degeneracy is broken. So actually, this was studied in 2020 by Héctor Olivares and collaborators, Luciano Rezzola, and where they studied the effective shadow of a scalar boson star, and they compare it to an accreting, so it's an accreting boson star, to an accreting Schwarzschild black hole.
Sorry, Nico, I have a question.
Yeah, of course. Go ahead.
Why these stars have shadows if light doesn't interact?
Yeah, actually, so the thing is that for some models, you have that all the matter, all the luminous matter, let's say, doesn't fall to the interior. Instead, the circular or the last stable circular orbit is not at r equals 0. So you have something that is around the Proca star at 2m actually, sorry, 6m. So you have an effective shadow because all the tori is not formed inside the Proca star.
Okay, that I understand. But what is what blocks the light of the matter that is behind the star? Because light doesn't interact with these scalar particles, so I would assume that it goes through the star.
Yeah, it goes through the star. Yeah, indeed. So for example, you have here. That's why I've said that it depends on the observation angle. So here it's like 88, 86, I think. So you are like looking from so this is basically the equatorial plane, and this is the tori.
Mm-hmm.
Yes.
Okay. Well, let's go on.
No, but I think, I mean, let me. It has a photosphere. That's it.
Yes.
So if it has a photosphere, whatever crosses the photosphere will not go out from there. It will just. I mean, this is the last circular photon orbit by definition. So everything that comes, it looks like a black hole. Everything that has a photosphere looks like a black hole. Everything, so it looks dark, even if it. So if it has a photosphere, it's indistinguishable. This is why it's called a mimicker. It's indistinguishable from a black hole. So everything that goes, spins, and gets trapped inside the photosphere. So light doesn't get trapped inside the horizon, it gets trapped inside the photosphere.
Yeah.
That's the reason.
Can I go on?
Yeah.
Okay, thank you. If you have any question, you can interrupt me at any time. So okay, so also in this for this event GW190814, which corresponds to the coalescence of a 23 solar mass black hole with a 2.6 solar mass compact object, in the paper of the collaboration, it is said, of the LIGO-Virgo collaboration, it said, our discussion has thus far neglected the possibility that a secondary component is an exotic compact object, such as a boson star or a grav star, instead of a neutron star or a black hole. So our analysis does not exclude this hypothesis for the secondary. And in one of the Event Horizon papers, they also discuss about these black holes with scalar wigs or hair. So it's basically rotating Kerr black holes or Schwarzschild black holes that have a large amount of scalar field or bosonic field around the black hole. And it can be even in equilibrium with the black hole. So we have a stable Kerr black hole with bosonic hair. So while the shadows of this class of compact objects are expected to be similar to Kerr, and therefore cannot be ruled out immediately by current observations, the most extreme examples are not viable models for M87. So let me say that in both the two big experiments, current experiments regarding strong gravity, and strong field regime of gravity, so the detection of gravitational waves and these shadows by the Event Horizon telescope. So boson stars, or at least bosonic fields, are discussed as a possibility, as a viable exotic compact object candidate that mimics these black holes up to some point. So why bosonic fields? Why ultralight bosonic fields and boson stars? Why dark objects? Well, we know that dark matter is up to 27% of the energy content of the universe, and we do not know what dark matter is. So it could be ultralight bosonic fields, could be boson stars. In a cosmological context, scalar fields have been proposed as constituents of dark matter halos in galaxies, and this is because for this ultralight boson particle with this mass, 10 to the minus 22 to 10 to the minus 24, the masses of these boson stars, of the gigantic boson stars, will be of the order of dark matter halos masses, and the radius, the Compton wavelength, is also of the order of kiloparsecs, and is of the order of the radius of dark matter halos. And supermassive black holes at the center of the galaxies are not a threat to these scalar field dark matter models, because they can develop quasi-bound scalar field configurations that may be very long-lived, that have been called scalar wigs. And recently, Carlos Herdeiro and Jean Radu found that astrophysical rotating black holes or Kerr black holes could have scalar or Proca hair. This bosonic field that it's around, it's rotating with the Kerr black hole, and it's in equilibrium with the black hole. So forming another type of object, a Kerr black hole with bosonic hair. And from a particle physics point of view, we have I'm not an expert, but we have from string theory, we have these axiverse also coming from quantum chromodynamics, from the axion and axion-like particles. So coming from the axiverse, these ultralight bosonic fields could have masses between 10 to the minus 33 to 10 to the minus 10 electron volts. So I think it's becoming increasingly clear that scalar fields, or at least vector fields, could have a great impact in many areas of astrophysics, of theoretical physics, of high energy physics, and of cosmology, becoming a link between these different fields. So numerical studies can be undertaken to make predictions and understand the properties of bosonic matter and of bosonic stars. So now we'll talk about isolated boson and Proca stars. We'll discuss their stability and mechanisms to their formation, to their dynamical formation. So if you build the sequence of equilibrium configurations in spherical symmetries, so without angular momentum, you get this type of figures, of plots. So basically you have a maximum mass. This is for the scalar boson stars. For Proca stars, it's the maximum mass is slightly larger, it's 1.05, and depends on the inverse of the particle mass mu. So we have this maximum mass, and then we have two branches. And there is a parallelism, a very nice parallelism with neutron stars and white dwarfs, so with fermionic compact objects, because we also have this maximum mass for these neutron stars and white dwarfs. So this is the Chandrasekhar limit mass, but also we have this stable branch of stable models against linear perturbations, and we have branch after the maximum that becomes unstable. These models become unstable and can collapse or disperse or migrate, and that's the same for bosonic stars. So we have these two branches. And there's a further parallelism, because for neutron stars, well, we know that the maximum mass depends on the equation of state for neutron stars, the dense matter equation of state that we do not know yet. So, and this is the case for bosonic stars, because it depends on the mass of on the particle mass. So depending on this particle mass, we can have different maximum masses. If we perform nonlinear simulations using numerical relativity and numerical relativity codes and techniques, then we can study the stability of these stars. So we see that the models in the stable branch are indeed stable for a very long time. Even if we introduce some initial perturbation, then they will oscillate. For both cases, neutron and boson and Proca stars. The models in the unstable branch, they can collapse and form a Schwarzschild black hole. And for bosonic stars, they can also disperse because there is an excess mass, so it's not bounded. And it can migrate to a stable configuration and start oscillating around this model. So we have models of bosonic stars that are stable, just like neutron stars. But it's not just like proposing some exotic compact object. So we have to study not only the stability, but try to find a formation scenario in which the stars can form dynamically. And for scalar boson stars, in 1994, it was Seidel and Suden that were studying boson stars with numerical relativity that found that they could form through a mechanism that they call gravitational cooling. So this is the picture. You have this scenario is you start with some dilute cloud of scalar field with a large mass that can be larger than the maximum mass, than this 0.6. And you evolve it, and you see that from the incomplete collapse, gravitational collapse of this cloud, you form, that doesn't collapse to a black hole, it's not compact enough, but instead you form a compact object that resembles very much to a boson star with the same parameters, with the radius, with the mass, and with the oscillation frequency. the excess mass, the excess field is just radiated away through this gravitational cooling. So not all the initial cloud can be bounded through the self-gravity of the newly formed boson star, but it's just radiated away, the excess field. So in 2018, a master student at the time, which is now a PhD student, Fabrizio Di Giovanni, we repeated the same scenario, dynamical formation scenario, but now for a vector field and for Proca stars. So we start with this dilute spherically symmetric cloud of vector field that collapses quickly, and you form a compact object at near the origin of your computational grid, and the excess field, the excess energy of the field is just radiated away through this gravitational cooling. So
Nico,
if you look, yes, see?
Can I ask you a question? Sorry, because I entered late, but I guess, I mean, this boson star is a complex.
Yeah, it's a complex. Yeah.
That has some rotation in phase, no? The phase is rotating, no? So in this way of collapsing, this angular momentum, it's an initial condition, or is something that is produced?
Well, I will talk about angular momentum later, but this is non-spinning. This is spherically symmetric.
Okay, but then if you will not the spin, the internal angular momentum, the one you need. I mean, this is an initial data.
Yes. So you start. I guess it's spin 1 and spin 0, right? This is a vector field. You have to start with a vector field to form a Proca star.
Well, I was thinking of the boson star, the normal boson star. So in the case of a boson star,
yes,
you also have this mechanism here.
Yes. So it's the same. It's basically the same.
You start initially from a cloud of a scalar field, which is complex and which has the phase is linearly rotating.
Well, in this case, it's not rotating. It's just so the answer for a scalar boson star without rotation is this one, where this is a function of R.
Yeah. So, but this omega is there from the beginning.
Yes.
In the collapse.
Well, yeah. So actually, you start your initial data. It's a complex field. So you put some. It's at t equals 0. So this part is just 1.
Yeah, exactly. But then this rotation in this complex rotation starts from there. So for the whole is homogeneous throughout space. Yeah?
Yes.
This is the omega you have there.
Okay.
Can you go to the previous to the curve of stable? This one, yeah. So this omega over mu here.
Yes.
So is this a dynamical quantity or this is an input?
It's an input when you try to form. It's like the central value, for example, of the density for a neutron star. So if you put like I don't know, 10 to the 15,
right. Yeah, I understand.
You will get some model.
Okay, so you start with a cloud, and then you pick one point in the axis here, for example, 0.909, no? And then you let the thing collapse, and it forms a boson star of the mass almost this 0.2 probably.
Okay, so I think now I understand your question. So no, in the dynamical formation you start with a cloud, but there is no input of this omega.
Where does it come from?
This omega comes from. It depends on the parameters of the cloud. If it is really compact, you will form more compact objects. Also in the total mass of the cloud. If it's larger than the maximum mass, you will get around here. It's smaller than you will get these solutions. But also depends on the. So you start with a Gaussian distribution for the field, for the scalar field.
Yeah.
And depending on the amplitude and on the width of the Gaussian, then you can get different models and different omegas, because depending on the final mass, you will get a compactness and an omega. So it's not an input. It's not like I want to form this model. So I put like omega equal 95, and I form that one.
So at t equals 0, you put no omega 0, just a phi 0, no omega.
Yes. Yeah.
And as it cools down, it starts spinning. It starts I mean, it's
Yes,
rotating in
yes,
the compass
exactly.
plane, and it adjusts dynamically to the value in this axis that, okay.
Yeah, the more compact, the smaller is, the lower the omega, sorry.
I'm trying to understand what's the mechanism to make this omega. It's very unintuitive. What sets this omega to be non-zero?
Well, it's the compactness. If you can, if you start with some model that can form these compact stars, then you need a low omega that can support the gravity of the field itself.
Yeah. Okay. Thank you.
Okay. So yeah. So I was saying that then, if you look at the radial profile, what we actually form is a perturbed Proca star that is oscillating radially. That will eventually relax to the static Proca star solution, but it's oscillating around this Proca star solution with the same parameters, with the mass and with the oscillation frequency. And let me also add that we can form actually mixed fermion-boson stars. So having, like, if we assume that the fermion star is a neutron star, a compact neutron star, then we can have solutions which are a neutron star with a core of bosonic matter, which is a boson star, really compact boson star, or even a neutron star which has an envelope of bosonic matter, of a boson star. Can form these mixed configurations. And people have studied the properties, the stability properties, the dynamical properties of these stars, and we have also studied the dynamical formation. So we can start with a formed neutron star with some mass. We put a dilute cloud of scalar field, and the neutron star will start accreting this scalar field, and the scalar field will also collapse in itself, and you can form this mixed configuration. Also, there is a nice property. There is an extended stability, in the sense that there are boson stars that are in the ground state, in the fundamental state, but then you have excited models that have more mass, more energy, and that they have this node in the radial profile of the scalar field. So these excited states are actually unstable when they are isolated. So they decay to the ground state, they lose the node, and they lose part of the mass, or they can also collapse to the black hole. They are basically unstable. But if we put it inside these excited states a neutron star, they become stable. So there is this cooperative stabilization mechanism in which a central object, which is stable, a compact object, such as a neutron star, can stabilize an excited boson star. This was also seen for, instead of having a neutron star, having a ground state boson star, which is a field independently of the other field, scalar field in the excited state. Okay, now about spinning bosonic stars, in the sense that they have angular momentum. So now the Proca field and the scalar field answer is a bit more complicated. So we have this harmonic dependence, but we have also this dependence with phi, with the theta and phi, which can be seen as a spherical harmonic. So basically, we have spinning models, so boson stars with angular momentum, for those models that have m different from 0. So m equals 0 are the static objects without angular momentum, with total angular momentum. And then m equal 1, for example, this is n equal 1, so it's the ground state. The m equal 1, n equal 1 is an excited state. Let's focus on this one. So you have this dashed red line, which correspond to spherically symmetric non-spinning Proca stars, and you have this m equal 1, which are spinning Proca stars. But actually, the angular momentum is quantized, in the sense that there is nothing in between these models. So each model, which is determined by this oscillation frequency, will have a mass and a pair of m and j, where j is the angular momentum. So,
Nico,
yes.
So in this curve, are they all stable, or beyond 5 they're unstable?
Beyond 5? Sorry. Beyond here. Yeah. So yeah, I will talk about the stability of the spinning bosonic stars a bit later, because there's a few things to comment. So I can say that yes, these models are so if you look at this, you have the maximum mass for spinning Proca stars, and then this would be the unstable branch. Okay, this will be the stable branch. But for example, as I was saying, This also, you can see that this is the maximum mass for these excited states. So this, in principle, should be a stable branch. So these models here should be stable. But actually what we see is that they aren't stable. They decay to the fundamental branch, or they collapse to black hole.
Okay.
So having a maximum mass and 2 branches is not enough to claim instability.
Okay. But if one branch is stable, typically it tells you that the other side has to be unstable.
Yes. Okay, so I was saying that bosonic stars, we can have these spherical harmonics, and actually we can have different solutions of bosonic stars depending on the your input of the spherical harmonics. So for example, for a scalar spinning boson star, if you put an L equal m equal 1, or L equal 1 m equal -1, so you get this shape. It's like a torus, like a donut, let's say. But also we can play with the spherical harmonics, and if we take the L equal 1, m equal 0, instead we can get boson stars that have this dipolar shape, this kind of, it's like a peanut shape. And in this case, since m equals 0 is equal to 0, then it's non-spinning, it doesn't have a total angular momentum. It's an static solution. So if we look, let's focus on the m equal 1, L equal 1, m equal 1 bosonic stars. If we look at the morphology of the energy density for Proca stars, then we have something that is spheroidal, with the maximum of the energy density at the center. While for scalar boson stars, the m equal 1, it's toroidal. So the maximum of the energy density is away from the center. So let's try to address the stability of these stars. So for both of them, we have these 2 branches. We have a maximum mass, we have a stable branch, and a stable branch for both Proca and boson stars. So let's try to evolve a model of a spinning scalar boson star in the stable branch. So we perform this nonlinear simulation, so with the full Einstein-Klein-Gordon system. What we see is the following. For a long time, the star is stable, it stays just there, as expected, but sometimes there is this, around 1000, there is this non-axisymmetric instability, I will start it again, that kicks in, actually destroys the star, destroys the shape of the toroidal shape of the star, and the star is compact enough and it collapses to a black hole. Now, if we try to form from this spinning scalar boson stars from a dilute cloud, but now with angular momentum, with this shape, so it's an m equal 1. What we see is first there's the collapse. We form something that stays there, but at some point there is also this non-axisymmetric instability. There is a fission into blobs, into pieces of the star, and then it decays to something which is a highly perturbed, spherically symmetric, non-spinning scalar boson star. So during the process, all the angular, or almost all the angular momentum is just radiated through gravitational waves and the loss of mass and of scalar field. Now, if we look at spinning Proca stars, again in this stable branch, just like for spinning scalar boson stars, even if we add this large initial perturbation, non-axisymmetric perturbation, to try to trigger some hidden non-axisymmetric instability, what we see is that it really quickly recovers its shape, its spherical shape, and it stays there even if it's perturbed. So basically, this what we are seeing, and we can also form m equal 1 Proca stars, spinning Proca stars from the collapse of a spinning cloud, of a spinning dilute cloud, and just our solution starts oscillating around this stationary solution with the same mass, angular momentum, and oscillation frequency. So basically, this is telling us that m equal 1 Proca stars, spinning Proca stars, can be formed dynamically and are stable. The models in the stable branch are stable against linear perturbations and against this non-linear, non-axisymmetric instability. But on the other hand, we have that m equal 1 scalar boson stars. If we try to form them, even from the merger of 2 non-spinning scalar boson stars, what we get at the end is a spherically symmetric boson star, because all the angular momentum is just radiated away. And if we try to evolve a compact stationary model, what we get is also this non-axisymmetric instability and the collapse to a curved black hole. So basically, m equal 1 scalar boson stars are unstable against these non-linear non-axisymmetric instabilities. So, so first we thought that this could be this stability instability, could be related to the type of field, of bosonic field that we are evolving. So a vector field may give rise to more stable configurations, while a scalar field gives rise to these unstable stars. Or it could be that it's related to the morphology, to the shape of the star, like having the maximum of the energy density at the center. It makes the star more stable than having this toroidal shape. That depends very much on the angular momentum. So if there is a small loss of angular momentum, then the whole star, the whole system is compromised. So it turns out that M=2 Proca stars also have this toroidal shape in their energy densities. So we try to form an M=2 Proca star, and what we saw is that they also suffer these non-axisymmetric instabilities. So there is this fission, this formation of two blobs, and then the decay to only one, this object. But it turns out that it's not a non-spinning Proca star. It decays from an M=2 to an M=1. So the Proca field can retain part of the angular momentum, and it decays to the M=1, and not to the non-spinning. At least this configuration that we studied. So let me also add this parallelism again with neutron stars, because this non-axisymmetric instability has been extensively studied for neutron stars. It's a very well-known instability. It's called the bar mode instability. Basically, for quasi-toroidal neutron stars, you can have also this bar that forms, and then it starts emitting gravitational waves, and it decays to something which is spheroidal. It can retain part of the angular momentum. So if you look at the time evolution of the modes of the instability, you see that this is for neutron star, for these neutron stars, this is for the boson stars. You see that first the M=4 dominates, but then it's the M=2 that grows exponentially till it reaches this maximum, and then the star is just destroyed, and it decays to the non-spinning scalar boson star or to this spheroidal one. So it's very nice to see this type of instability in both type of stars that are described by these two really different type of matter, of bosonic and fermionic matter. So it's more related to the shape, to the morphology of the energy density, rather than to the matter, to the type of matter. So this could be a way of distinguish between stable and unstable exotic compact objects, because it's not related to the type of matter. Okay, so I have discussed the stability of isolated both rotating and non-rotating bosonic stars. So now let's put them in a more interesting scenario, astrophysically speaking. So in binaries, let's perform mergers, and let's compute the gravitational waves from these mergers. So let me say that Carlos Palenzuela, Luis Lehner, Liebling, Miguel Bezares, Carles Bona, Vitor Cardoso, Paulo Pani have been studying these head-on collisions of bosons, of scalar non-spinning boson stars in orbital mergers, also computing the gravitational wave signatures in dark boson star binary mergers. So basically studying the scalar case. So I focus on Proca stars, on vector fields, and I started by doing some equal mass head-on collisions of non-spinning Proca stars. And what you see here is that these three models that are more compact, you see that after the collision, after colliding, they collapse and form a Schwarzschild black hole. But this one that is not compact enough to form a black hole, instead you form a more massive, more compact Proca star. So we can compare the gravitational waves from this equal mass Proca star collision to an equal mass black hole head-on collision with the same mass than the Proca star. And for example, if the Proca star collapses before the collision, before colliding with the other Proca star, what you get is actually a black hole collision, and just get the same waveform. But if we look here, we have this so the Proca star after colliding forms the same Schwarzschild black hole, or almost the same Schwarzschild black hole with the same mass. So actually the ring down is the same than for the black hole collision. But then if you look at the pre-peak, the pre-collision, pre-peak, the pre-collapse, sorry. So what we see that there is this difference. There's the signal is different with respect to the black hole collision. So even if we can mimic the ring down, well, we are forming a black hole, so it's not really mimicking. We are forming a black hole which is ringing. But to differentiate between these two models, then we can look at the pre-peak signal. Okay, so after that, well, I started studying the stability of spinning bosonic stars. So it turns out that spinning scalar boson stars are, at least the mini boson stars, are unstable. So I've been doing some head-on collisions of spinning Proca stars. So you see here the two Proca stars that come together, they collide and form a curved black hole. And we can compare the gravitational waves from the head-on collisions of spinning Proca stars and curved black holes. So you can see here the head-on collision of two curved black holes. You see it's basically the peak of the emission and then the ring down. But for Proca stars, you get a longer and richer signal from head-on collision.
Sorry, can I, well,
Yes.
Is there a comparable result from scalar bosonic stars? And could one plot that?
For scalar boson stars. So, well, at least for mini boson stars, because people are studying and seeing that if you put some nonlinear potential, like 5⁴, then you can get models that are stable, but no one has done these simulations. So we do not have waveforms from spinning scalar boson stars, because mini boson stars are unstable. So they couldn't form and you couldn't get them to be together and then collide. That's why we did Proca stars.
Okay, but non-spinning?
Yeah, non-spinning. So people have done non-spinning solutions.
Okay, so in principle you could plot that and also compare it.
Yes, and even quasi-circular mergers. So people have done also.
Yeah, sure. You mentioned this. Oh, okay, right. Thanks.
Yeah. So yeah, I will say why we are doing head-on collisions and why of spinning Proca stars. So a bit later when I discuss GW190521. So and then you have models that they are not compact enough to collapse to a black hole, so we do not have the ring down. We just have this continuous emission of low frequency gravitational waves. So these last months I've been doing a lot of simulations. We have like more than 300 simulations of spinning Proca stars, head-on collisions of spinning Proca stars, computing the gravitational waveforms. And now we have built this catalog of signals from these bosonic stars. And actually, you can see here, so from 0.8, which is the more compact model that we have evolved, to 0.93, you will see how the gravitational wave changes with the compactness, basically. See how the properties, the features of the signal change with the compactness. And after that, it would jump to the previous kind of this type of signal. Okay, so we have this catalog of Proca signals. So we wonder if we could compare, we could feed with our Proca star waveforms any real gravitational wave event to see how well we can feed these events. But it turns out that almost all the events detected so far by LIGO and Virgo are similar to the first one, to GW190521, which is basically a quasi-circular compact binary merger of two non-spinning black holes. So we have three distinct phases. We have the spiral phase, in which the two objects are orbiting around the center of mass. They are getting closer due to the emission of gravitational waves and the loss of angular momentum of the system. Then we have the last orbits with the plunge and the merger, that this part of the signal can only be obtained using numerical relativity techniques. And then the formation of the final black hole and the ring down signal with the exponential decay. So we look at GW150914. So it's basically this type of signal. It's very clear, very, very nice. So we have some of the cycles coming from the spiral. Then we have the peak and the ring down. So this is a chirp type of signal because the amplitude is like a bird. So we have that the amplitude and the frequency are growing with time until we reach the merger, the plunge and the merger with the peak of the emission and the ring down. So we cannot really expect to feed with our head-on collisions of Proca stars because these signals, because we do not have in head-on collisions this part, this spiral part, which is a which is a large part of the signal detected. But then we have the rather special event, which is GW190521. And I say that it's special because it's the most massive binary ever detected, with a final mass of the black hole, which is the first direct detection of an intermediate mass black hole with 150 solar masses. Moreover, it's the most massive colliding individual black holes, with the masses of these black holes within the pair-instability supernova gap. And as you probably know, this challenge current stellar evolution models. So there is no clear formation mechanism to have these black holes with these masses. So it's also a bit special because it's a precessing system, in the sense that the spins of the individual black holes are not aligned with the orbital angular momentum. So we have precessing motion, and we have a modulation in the amplitude of the gravitational wave signal. So if we look at the signal morphology of GW190521, we see that it's completely, it's different to the first one, to the chirp signal, to GW150914. So we see in this case that there is almost no pre-merger, pre-peak signal, so there is almost no in-spiral part. And it's just really like a burst a short burst of gravitational waves. So it could be that, being the most massive ever detected event, it could be that the frequency, so we go to the low frequency range compared to GW150914, which we can see. So this signal, we have a large part of the in-spiral phase, the merger and the ring down, that fall within the sensitivity of LIGO and Virgo. But for GW190521, then it could be that the spiral part is just behind this wall at low frequencies, which is we have not enough sensitivity in the detectors to see this part. So it could be just that we cannot really resolve that part in the detectors. Yes?
So I just want to point out this bullet point, the GW signals, etc., lack the in-spiral. This isn't really true. I mean, the GW signal is whatever it is, and it could have an in-spiral. The problem is when you filter it through the detector sensitivity, you can't see it anymore. So, it depends how you define the signal, but
yeah, for sure.
Okay.
Yeah, thank you, Thomas. So it could be that we cannot just, there is an spiral, but we cannot really we cannot see it, or it could be that the signal is really short. It's just is this. So people have proposed alternative scenarios, like with Juan, Alejandro Torres, Professor Tony Font, we studied also head-on collisions of Kerr black holes to try to explain this signal. And also people have studied highly eccentric, not head-on collisions, not extremely eccentric, but highly eccentric collisions of black holes. And in principle, they could also explain this signal. So we tried first, so we performed these head-on collisions of Kerr black holes, and we tried to feed this signal with our waveforms of Kerr black holes in a head-on collision. But you can see here, so it's the green dashed line. You can see that we can feed the peak and the ring down, but not really the pre-merger, the pre-peak part of the signal. So we thought, what about Proca stars? What about these matter stars that can be massive like these black holes, and that they do not collapse right after the collision? So you form an hypermassive Proca star that will emit gravitational waves, then collapse, form a black hole, and then we can have this ring down part. So we did that. We did equal mass Proca collisions and equal mass Proca collisions, and you can see here the red and the blue lines that can feed the signal quite well. So we performed, it was Juan who did it, so we performed this Bayesian analysis of using Proca stars of GW190521, and actually we got really similar, the same parameters than the analysis with binary black hole merger. So this is an redshifted mass of 250 solar masses and a really high spin of 0.8, 0.7. And the thing is that spinning Proca stars, since they do not have an horizon, then they are not limited by this, the Kerr limit, the a dimensionless spin equal to 1. So the A, which is m divided by j squared, can be larger than 1. So actually in a head-on collision, in which you do not have the extra angular momentum from the spiral, then you can form highly spinning Kerr black holes because these Proca stars are storing a large angular momentum, which is not the case for black holes. So we performed this Bayesian statistical analysis using our models of Proca stars. At the time, we had only like 40 waveforms and 40 for the equal and 40 for the unequal, but yet we obtain a slight preference in our Bayesian analysis with respect to the binary black hole. So it's not enough to claim this is a Proca star, but it's really nice, and even slightly better fitted. Our Proca star waveforms could slightly better fit the signal than this quasi-circular binary black hole. So of course, as I was saying, this is not a strong evidence of anything of Proca stars, but I think it's very nice. It's the first the first time that clear degeneracy in the emitting sources of a real gravitational wave event is shown. So even if, well, it's not sure that it is of course a Proca star merger. And as a proof of concept, if we assume that the Proca hypothesis is true, then that this is really a Proca star merger, then we can compute the mass of the particle that compose the bosonic particle that compose these bosonic stars. So what we obtain is that if this is really a Proca star merger, then there is an ultralight bosonic field with this mass, which is around 9 times 10 to the minus 13 electron volts. So I think it's really cool. It's really nice, this result, because it's a synergy between different fields, between numerical relativity, numerical simulations, the fact that obtaining and proposing these spinning Proca stars, these exotic compact objects, studying their stability, their dynamical formation, then gravitational wave astronomy and data analysis, and then obtaining this boson mass, which is related to cosmology and particle physics. So it's really a very nice result. So in the masses in the stellar graveyard, so this is GW190521. This is before the second release of the gravitational wave catalog. So it could be that GW190521 is not. It could be, of course. I mean, it's not sure that this is actually a Proca star merger, and what we have is actually this alternative stellar graveyard with boson stars that form this massive intermediate mass black hole, and they are composed of this boson particle with this mass. So of course we have been doing head-on collisions, but well, the next step is to perform quasi-circular mergers. And actually this is still eccentric, so it's a superposition. We get a boost stars that they perform almost an orbit. It's not a quasi-circular merger, but still we have these nice waveforms. And actually if LIGO and Virgo and CAGRA could detect these waveforms that in principle couldn't be emitted by a black hole, because the stars collide here. So this is a perturbed star that is oscillating and emitting gravitational waves until it collapses and we get the ring down. So if we can detect this type of signal, then we could really claim that we are detecting bosonic stars, or I mean, maybe bosonic stars is just a toy model for a more complicated dark matter or dark object. So in conclusion, I'm going just to finish that gravitational waves from boson star binaries, from bosonic star binaries, could be used to detect ultralight boson particles, so using GW190521, but other intermediate mass events. So gravitational wave detectors could become particle detectors. So is there ultralight in the dark? And maybe it is time to Proca and roll. So thank you very much.
Thank you very much, Nico. That was a great talk. Are there any questions?
So I have a question. So you need a mass for this vector particle, which is how much? 10 to the minus 13 or something like that.
Yeah, 10 to the minus 12, let's say.
Is this really a sharp demand, or is this a lower bound or an upper bound? Can you compensate a higher mass with something or a lower mass with something? I don't know.
Yes, good question. So actually, it's not it's neither an upper bound or a low bound or lower one, because it's really like a measure of the mass. So if this is a Proca star and it's really a head-on collision, then we can, like, with fitting our models with our masses, then we can get the mass of the particle. But then, of course, this can be compensated because this is mini Proca stars, in the sense that the Lagrangian is just mu square, phi square. But we can introduce higher order terms like phi to the 4 with lambda phi to the 4. And then we can get more compact and more massive stars just playing with, if we fix the mass, we can play with this lambda and get larger masses, maximum masses and larger compactness.
Okay. Yeah, I'm not aware of this business, but I mean, people is trying to constrain people in dark matter, constrain these masses severely, and there must be. I mean, I guess you have checked if these numbers collide with other constraints in dark matter.
Yeah, that's a very interesting question, because actually they collide. So these masses, so there are these studies that they constrain the mass of ultralight bosonic particles, of ultralight vector boson particles, through the because you have this super-ion process with ultralight boson particles that they can extract the angular momentum, and then they dissipate it through gravitational wave emission. So if you see a black hole that is highly spinning, at least you can constrain mass range for these bosonic fields. The trick here is that it's for real fields, and this is a complex field, because so both fields, both real and complex, can suffer this super-ion instability process. So they extract angular momentum from the black hole, spinning down. But then at the end point of the super-ion instability, for a complex field, you can form a system which is stable. It's a Kerr black hole with bosonic hair, which is because the field is complex. Then the solution, the stress energy tensor, is time independent and axisymmetric. So there is no gravitational wave emission. And actually, even if the black hole has lost angular momentum, the bosonic field around the black hole can store that angular momentum. For a real field, it's different, because then the solution is no longer axisymmetric, and you have emission of gravitational waves that can just dissipate the angular momentum of the black hole. So, I mean, I'm not saying that we cannot, that those we have not to take into account those limits, those constraints for real field. The thing is that I'm not sure that can directly apply to complex field.
Okay.
Can I add an extra comment to Javier's question? So the value of the mass we get is also degenerate potentially with the eccentricity of the orbit. So in this case, we are restricting to this head-on case, and that restricts a lot the spin that the individual stars can have. If we manage to do these quasi-circular mergers, then the spin of the stars could be different, and therefore this range for the mass could be broadened. So this is a kind of over-restricted estimate. But as Nico said, we don't know if it's a lower or an upper bound. It's just consistent with whatever the true measurement would be.
All right.
Sorry, can I ask something?
Yes.
So, okay, did you look at did you try to do let's say, parameter estimation or whatever calculation with just head-on black hole collisions?
Yes, yes. So basically, well, it was Juan, so maybe Juan can reply, but basically the log B was much smaller than the others.
Okay, I mean,
Yeah, you have it here.
the generic question is like you have head-on black hole collisions, you have head-on non-spinning boson star, let's say scalar boson star collisions. You could have things with scalar bosons, vector bosons, fermions, etc., etc. So how, I think the general question is like, how big is the parameter space of these like exotic objects, and how far do you have to look before you know? Before you have some idea of like, well, have you got really the best model?
Yes. So well, regarding if you kind of fix your model, like it's a mini boson or mini Proca star. So you have, these are the models that you can have for the spinning case.
Sorry, I mean the question I'm asking is, in general, one could have a theory with scalars, with fermions, with vectors, with everything. Is there a program to explore this much bigger space, or you just want to do something, let's say, simpler things one by one?
Yes, for now, I mean, we restrict ourselves to Proca stars because it's, I mean, we saw that it's the model that is stable, but now there's people that have found that if you complicate a bit the model of the scalar field, then you can get also stable spinning solutions. So I think it would be really interesting to expand this study now for spinning scalar, for the scalar case. And yeah, I mean, and there's a lot of possibilities with boson stars, like having different type of objects, having superposition of boson stars. So yeah, I mean, we plan to study first the stability and then perform these collisions and computing the gravitational waves.
Yeah, okay, I guess there's, well, might have different priorities in terms of like going to, non-zero, well, orbital. Okay, at the moment you have like maximum eccentricity. So as you said, I think the astrophysically interesting case may be to look at the, let's say, eccentricity less than maximum to start with, because you can't constrain, I mean, you can't force, if there are these things hanging around the universe, you can't force them to collide head on with each other.
Yeah.
So yeah, I mean, in terms of, let's say, reducing the number of simplifying assumptions you need to make, I mean, okay, it's possible that if these things are real, then it's possible that if there could be a simple theory, and the simple theory could be just, well, you have a single vector boson, which is reasonable, but then still, I mean, astrophysically, you expect to like full range of eccentricities, or maybe you expect some particular distribution.
Yeah.
Okay.
So doing head-on collisions, it's more related to a computational problem, in the sense that doing quasi-circular mergers is not easy, and also that we do not have like the appropriate initial data for doing these quasi-circular mergers. So we have to, right now we are just putting the two stars together and we evolve that.
Yep.
So, but we have to solve the constraints to the Einstein equations to have the true initial data.
Right, but I mean, I think, if these things do exist, then you would be predicting, I mean, I guess you're predicting that they merge, that they do actually produce mergers with all sorts of different orbits, or big range of different values of eccentricity. So I think that's, that could be the first sort of prediction to be tested.
Mm-hmm. Yeah.
Okay,
yeah,
great. Yeah, I mean, I understand that there's a huge amount of like computational work that has to go into this stuff.
Okay, I have a question. To simulate the spinning Proca star, are you using Fitisol Capsule or other spectral methods?
To get the solutions, yes. So it's not me who is getting the solutions. It's Carlos and Eugene who are experts on obtaining this kind of solutions of compact objects. So yeah, it's Fitisol, yeah. And but for the evolution, it's not. It's the Einstein toolkit.
Okay,
so the questions are not elliptic; they are hyperbolic. So it's the BSSN formulation is different. So it's that time evolution. It's not obtaining these solutions only.
Okay, thank you.
I have a question.
Yes.
So at some moment you pointed out that the images that the Event Horizon Telescope took of M82, I mean, could be reproducible by boson stars because you can estimate the effects of the shadow and all of this. But this was, as far as I know, rather assessed via just comparing pictures. You know if there is any quantified way of stating how similar those pictures are and at what point they could be distinguished from each other?
So yes, actually, well, for the Event Horizon Telescope, well, there's people saying that it could be boson stars, but in the paper they talk about black holes with scalar wicks, which is it's a black hole. It's really a Kerr black hole and having some cloud of well, bosonic field around it. So it's if it's massive, if it is a light in the sense of not really massive compared to a black hole, then the geometry is Kerr. So the shadow is the same. That's why they see shadow of this class are expected to be similar to Kerr, cannot be ruled out. But the most extreme examples in which all the mass or a fraction, a comparable fraction of the mass is inside the cloud, then the geometry is different. It's not Kerr, it's Kerr with bosonic field. So the shadow is different. And let me, so I might have them, yeah. Oh, sorry. So in Aveiro, we have Pedro Cunha, Carlos Herdeiro, and Eugene Radu that are experts in the computation of these shadows from these objects. So here you can see this is not a Kerr black hole with bosonic hair. Is actually a spontaneous colorized black hole, but you can see that there is almost no difference depending on the parameters of the model of the spinning black hole and different things. But yeah, and so it will be great to like perform these MHD simulations that they do at the Event Horizon collaboration to see if these alternative models could also like produce the same shadow, but those are extremely expensive, and yeah, I'm not sure if the collaboration is planning to do those simulations.
Okay, thank you.
Okay, if there's no more questions, then let's thank Nico with a round of applause.
Thank you very much. Thank you very much for your attention
Thanks,
and for the
Nico.
questions.